Welcome to the course Compiler Design. In this lecture, we are going to discuss about recognition of tokens. So in our earlier lecture, we discussed about specification of tokens, how to specify tokens. So now continuation of specification now, how to recognize tokens. So in this lecture, the outline is first we are going to discuss about as part of recognition of tokens. We will review once what is transition diagram, then how to construct transition diagram for tokens actually. Then recognition of reserved words like keywords and some identifiers. Then we will see some examples. Then finally, architecture of a transition diagram based lexical analyzer using transition diagram. So here the concept of transition diagram like automaton is used here for recognition of tokens. So let us consider the following grammar for branching statement, that is if then else statement. So the grammar is defined as follows: statement equal to if expression means condition, then statement, or this is simple if, then second statement, or if expression then statement, else statement. So this statement consisting of else part also, or null simply. So these are all the three possible cases for statement. Then here expression is the new here. Now what is expression here? So that is defined in the next line, next production. Expression equal to term relational operator term. RELOP means relational operator. So term relational operator term or term. Now what is term? The value of term that is defined in the next production. Term equal to ID. ID means identifier or a number. So if you can substitute ID or number in place of term, so you will get ID relational operator ID or ID relational operator term, like that. Then term value. So if you can substitute in case of statement expression means this value, then the statement will be changed accordingly. So this is the general grammar for branching statements. By substituting all these values, you can get different statements. So now here in this we used RELOP. This is nothing but relational operator. Here we use the comparison operators of languages like Pascal or SQL, where equal is equals, and whenever you can use this symbol, angular brackets with opposite direction, which is called as not equals. Now here in this grammar, you can observe what a grammar contains generally. Grammar equal to four tuples, V, T, S, P. Now here variables means the grammar starting left hand side, whatever the symbols. So now statement is a variable, expression is a variable, then term is a variable. Now same variables occurred in the right hand side also. Here see statement here also occurred, expression in the right hand side it occurred, then term it occurred in the right hand side. Now all the red color representation keywords. Here you can see if, then here else, then another one RELOP, then identifier ID number. These are all terminals. So now here the terminals of the grammar, which are if, then, else, relation operator, ID and number. So what all these terminals denotes the names of tokens as per the lexical analyzer is concerned. So now here terminals, here if is a terminal, then is a terminal. So again here new, else is a terminal, relation operator is also a terminal, then ID is also a terminal, then number is also terminal. Now VT, S means the starting production left hand side variable. So STMT is yes. Now P, set of productions. So these are all the productions. Yeah, this is P1, production 1, production 2, then production 3. Therefore, the nomenclature of the grammar with the 4 tuples G equal to VTSV. So all the tuple values are defined here. So now here, this is one example grammar for branching state. So now as part of recognition of tokens, so we know what is a token, what is a pattern, what is a lexium. You can recall once again. The patterns for these tokens are described by using regular definitions. So in our previous lecture, we already discussed. So what is regular definition? Regular definition nothing but a name to the regular expression. Suppose we have R1 is a regular expression, R2 is another regular expression. For R1 can be named as T1, that is regular definition 1, like that. So here also the patterns of these tokens are described using regular definitions as shown below. So in the previous grammar, so whatever the tokens we have, so what tokens we mentioned here, all the terminals are nothing but tokens, that is if, then, else, relational operator, ID and number. Now for all these, now we can define the definitions of tokens by using regular expressions followed by regular definition. So now here first the general definitions we will use here digits. So digit which consisting of 0 to 9 combination. Then we'll use other extra definitions also digits. So which will take combination of digit with positive closure excluding null by repeating 0 to 9 once or several times excluding null. So this is digit positive closure. Then number is defined as here. Here you can see here we have number is one token name, that is a terminal. How to define number? So unsigned numbers actually. So number is defined as with combination of digits. So that is digits means digit positive closure, then decimal point dot, then again digits. So then here it uses question mark operator followed by here it uses expression. Here E stands for expression, then not expression. So that is power exponent value. So E power positive or negative. It may use either positive or negative one at a time. So then again question mark operator, then again digits. So like that, for example, here you can take digits as 1, 2, 3.45. So the sum E positive again 0.5, something like combination. So like that, this is the number which allows with all combinations, that is floating point, then exponent value. So with the positive or negative all. So this is the definition of number. Then letter, we know letter means what it contains, both combination of uppercase letters and lowercase letters. Uppercase letters are denoted by capital A to Z, then followed by lowercase letters small a to Z. Then identifier. This also we know. Identifier, how to define the definition of identifier? It must start with a letter followed by letter or digit whole closure. This is nothing but L plus D whole closure, which allows possible in null also after letter. Then for the keywords, directly you can define with the same name only. For the keyword if only, the definition of the regular definition of this token. Then for then only, else only. Then for relational operator, you can include all the possible relational operators here. The first one is less than or greater than or less than or equal to or greater than or equal to or equal than or not equal. These are all possible relational operators. So these are all the regular definitions. Directly you can use the symbols. Then white space also, why? Because tokens allows white space also. So now white spaces are WS stands for white space. Here blank or tab or new line. Now you can see in the previous grammar. So whatever the tokens that is denoted by terminals, for all those regular expression definitions are defined. then those are all named with regular definitions. Left hand side names are called as regular definitions, then right hand side declarations are called as regular expressions. So now using these regular definitions further, so we will identify what are the lexemes, then what are the tokens, and what are the attribute values. So this also we already discussed in the previous class also, one example. Now with this grammar, now we will find all this again. Now here, lexical analyzer is summarized in below table, which shows for each lexeme of family of lexemes, which token name is written to the parser and what attribute value is written. So now here first lexeme means the given sequence of characters in the source program. Those are all called as lexemes. For each lexeme, you can mention the token name, then followed by attribute value. Attribute value is applicable only for identifier and numbers, and some cases for relational operators also. Now for white space, any white space, here no token name for this, no attribute value. Then if you can take the keyword if, the token name is also same if, then here no attribute value. Then for keyword then, the token name is also then, no attribute value. Then for keyword else, the token name is else only, then no attribute value. Then for identifier, you can use ID. For this attribute value is included. So the attribute value, what it shows, pointer to table entry. Table means the symbol table entry. Then number, if you can take a number, the token name is number, then again it has attribute value. So that is the addresses pointer to table entry, that is symbol table. Then for other lexemes, relational operators, you can take less than. So the token name is it gives the category of these operators. What type of operators all are relational operators. Therefore, the token name is relational operator, RELOP. Then the attribute value is written as the name of the symbol with capital letters. So that is less than. So less than is denoted by LT. This is nothing but less than. Then next one, less than equal. The token name is RELOP. LES stands for less than equal. Then next symbol is equal. Relational operator is the token. EQ. EQ is nothing but equal. Then next symbol is not equal. The token name is relational operator RELOP. Then its attribute value is capital N, capital E. That is not equal. N stands for not, E stands for equal. Then greater than symbol. Its token name is RELOP. Then it is defined by attribute value using GT. GT nothing but greater than. Then greater than or equal, the symbol, next symbol. Its token name is RELOP. Then it is denoted by GE. G stands for greater than, E stands for equal. So for the above grammar, the summary of lexical analysis with lexemes, token name and attribute values are listed in this table. So then move to transition diagram concept. So in finite automata, in the concept of automata theory, so here transition diagram and transition table plays major role. Every automaton, either finite automaton or push down automaton or Turing machine or linear bounded automaton, any kind of automaton as per Chomsky hierarchy, those are all denoted by using two pictorial representation. One is tabular representation, which is called as transition table, then diagrammatic representation, which is called as transition diagram. Now in lexical analysis for representation of tokens, we will use the transition diagram here. So as an intermediate step, the construction of lexical analyzer, we first convert patterns into stylized flowcharts, which are called as transition diagrams. Transition diagrams have a collection of nodes or circles called as states. We know this one. Then each state, here each state represents a condition that could occur during the process of scanning the input looking for a lexeme that matches one of several patterns. So now in lexical analysis, So what is the role of a state? So here each state represents a condition. What that condition contains, when that should be occurred during the process of scanning the input from the given source program, then looking for a lexeme. Lexeme means sequence of characters in the source program, further defines a token. Then that lexeme that matches one of several patterns, which gives a token. This is the purpose of a state of the transition diagram in lexical analysis. Then states are summarized to know about what characters we have seen between the two pointers. One is a lexeme begin and forward pointer. These two we discussed in our previous lecture in the concept of input buffering. So lexeme begin pointer and the forward pointer. Then what edges represents here in transition diagram of lexical analysis? So edges, we know edges are directed from one state of the transition diagram to another, which are all directed edges. Each edge is labeled by a symbol or set of symbols. That means one input or more than one input, separated with comma. Suppose we are in some state, yes, and the next input symbol is A, then we look for an edge out of state, yes, labeled by the input symbol A. Then if we find such an edge, we advance the forward pointer. Whenever such edge is found, then we advance. That means we have to move 1 point ahead towards right to the forward pointer. Like read or write header, movement of read or write header in finite automaton or any automaton, similar fashion. So the same purpose we will use here forward pointer and enter the state of the transition diagram to which that edge leads. Then enter the state of the transition diagram, next state where it leads or it goes to. Then we shall assume that all out transition diagrams are deterministic. So what is meaning of deterministic? That means there is never more than one edge out of a given state with a given symbol among its label. Nothing but from a state, we know the deterministic condition. From a state with one input symbol, so here there exists only one next state. So this is called as deterministic finite automaton. Suppose if we can take from a state with input A, it is going to Q1. Then again with input B also, it is going to Q1. See, from a state, so not with input B, with same input, if it will go to Q2. See, with same input from the same state, it is going to more than one next state. So this is non-deterministic finite automaton. So here we will consider the concept of deterministic finite automaton. That means from a state with given input symbol, it has only one next state. Then it doesn't allow a transition with null, that is epsilon or lambda. So that is deterministic automaton. So now here some important conventions about transition diagrams are there. The first one is certain states are said to be accepting or final state. This also we know in transition diagram. So what is accepting or final state? Then how this can be represented? These states indicate in lexical analysis that the lexeme has been found. So whenever it reaches to accepting or final state in the transition diagram of recognition of tokens, so whenever it sees a final state or accepting state, then it indicates that the lexeme has been found. That means automatically token is identified. Although actual lexeme may not consist of all the positions between the two pointers, lexeme begin and forward pointers. We always indicate an accepting state by a double circle, we know. So final state is represented with a double circle. And if there is an action to be taken, typically returning a token and an attribute value to the parser, who shall attach that action to the accepting state. So that is the first consideration in transition diagram. Now, second one, in addition, if it is necessary to retract the forward pointer one position, retract means it may move backward or forward with one position. That is, lexim does not include the symbol that got us to the accepting state. So in this case, then we shall additionally place an asterisk symbol near that accepting state. Suppose here this is accepting state. Near that, we'll put an asterisk symbol additionally in this case. This is second consideration. This asterisk symbol shows to retract the forward pointer one position. Then another one, the third consideration, one state is designated as the start state or initial state. So how to represent start state or initial state? With a circle, with an arrow, followed with a phrase start. This is the representation of start state. Initial or start state. It is indicated by an edge labeled with the phrase start entering from now here. The transition diagram always begins in the start state before any input symbol have been read. So these are all the considerations of transition diagrams. These 3 points also. The initial state representation and final state representation, then the movement of the state towards right or left. So this also we studied during the formal language and automata 3. Now let us see one example of transition diagram here for with respect to tokens. So the following figure is a transition diagram that recognizes lexims matching the token relational operator RLOP. In the above tokens, we already seen what are the various relational operators. Now for all these relational operators, how to draw the transition diagram. So using the tokens. Now we can see here first we have taken the start state. We have included an arrow labeled with the phrase start. Then here again final state is also same here. Now this can be labeled with state 0. Now here first you can take all the combinations. First less than. Then it is going to see one operator can be labeled in one edge only. One relational operator in one edge only. Then after reading one operator, it moves to the next state. Then it gives the next combination of operators. So whenever it starts with less than, what are the combinations we have? Next, less than equal combination is there. Then not equal combination is also there. With you can take opposite symbol. So now with equal, it goes to one accepting state. Now it returns the token name, relational operator followed by attribute value. So this is actually token specification. Here, this is the name of the token. Now this is attribute value. So it returns the token name is relational operator, then the attribute value is LE less than or equal to. So previously we already defined, you can recall once. So the same nomenclature are used here. Here you can see lexims token attribute value. So wherever relational operators, the token name is RELOP, then the corresponding attribute values, these symbols you can use. Same we are using here. So now here, the first case from state 0, 1, 2, it returns the token name relational operator, then the operator is less than or equal. Then if you can from state 1, if you can see the alternative, that is greater than symbol. So then it goes to other accepting state, let us say 3. Then what it returns here, if we can take the path 0, 1, 3, here less than, greater than. So here you will get the symbol less than, greater than. What is the symbol? This is nothing but not equal. So it returns relational operator as the token, then NE as the attribute value. Then other combinations. Suppose we want only less than. So now from state 1, it goes to other. So here retract. So the forward pointer may move one position. So at that time we can use asterisk near to that state. Then it returns, otherwise what it returns, relational operator simply less than, the attribute value is less than. Then coming to next case, starting with less than is over with all possibilities. Then starting with equal, from initial state, if it start with equal combination, what we have? Simply only one we have. It returns relational operator EQ, that is equal. Only one possibility is there. Then if it start with greater than symbol, next operator. With greater than also, again what are the other combinations we have? Greater than or equal is there. So if equal is there, then it returns RELOP GE, greater than or equal. Then otherwise, so with greater than, other combination, what we have? Only single symbol, greater than. Other, it goes to other state, then it returns relay operator GT, greater than. So again here retract. At that time we can use the pointer asterisk. Now this is the transition diagram for the token relational operator. So like for this we don't have any procedure here. Simply while drawing transition diagram for any token, what you have to do? You can start at one initial state, then you can take all the symbols in the token one by one as in one edge that can be labeled. Then it goes to next state, like all possible combinations you can take. Similarly for keywords, for identifier, for all tokens, we can draw the corresponding transition diagrams. So now let us see how to recognize reserved words, that means keywords and identifiers. So recognizing keywords and identifiers presents a problem. Usually keywords like if, then, or reserved. So they are not identifiers, even though they look like identifiers. The following figure shows transition diagram for identifiers and keywords. So again here you can see. So the start state. So the identifiers we know. For identifiers, the regular expression is letter followed by letter plus digit whole closure. Now how to draw for this regular expression automaton we know. First starting state. So here we continued the state numbers with the previous diagram. Here it's end with 8. So you can use any, why? Because finally we can take the final diagram with combination of all these tokens. So now here from state 9, first it must start with letter. So here we have taken as the edge labeled with letter, then letter or digit. Here L plus D whole closure. This is the loop. So next state on loop you can take a letter or digit, or you can take L comma D. So this loop denotes closure. Comma means plus. Then after this other. After L plus D whole closure other. There you have to retract the forward pointer. So then it goes to next state, which we'll call it as final state. Then for retract we can use the asterisk symbol. Then it returns the two methods. First method is called as get token. Then second method is called as install identifier. It returns the token with the two methods, that is get token and install ID. So this transition diagram shows identifiers and keywords. So here identifier, what are the identifiers? Actually letter or digit are the identifiers. Then these identifiers also considered as keywords also sometimes, like if, then, which looks like identifier, but those are all reserved words also. Here return. So return is the keyword actually, which is a reserved word. So like that, if, then, else also. So this is another transition diagram for identifiers and keywords. Now for keywords separately, we will see another transition diagram. So there are two ways we can handle reserved words that look like identifiers. First one is install the reserved words in the symbol table initially. Second one, create a separate transition diagram for each keyword. As an example for the keyword then is shown below. The first method is you have to install the reserved words in the symbol table initially, or you can create separate transition diagram for each keyword. The following example shows the transition diagram for the keyword then. Here you can see. So whenever you are drawing transition diagram for keyword, each and every letter in the keyword can be labeled in one edge. like relational operators, how we did. Now in the keyword, then you can separate all the letters one by one in the order T, H, E, N. All these you can label under each edges as inputs. Now first you can start with one state, which we'll call it a start state. Then it goes to next state. The first letter is T. Then next letter is H, that can be labeled in the second edge. Next letter is E, that can be labeled in the third edge. Then last letter is N, that can be labeled in the next edge. Now you can combine all these T, H, E, N like that. Anyway, you can start with at the start state, then proceed towards the accepting or final state. Now in that sequence, you can take all the letters, you can combine, then you will get again your keyword. So now other case, there is a retract here, non-letter or digit, then it goes to final state. Maybe after keyword, further there may be possibilities to have non-letter or digit, then it halts. So this hypothetical transition diagram for the keyword, then like that. Now here see, for keywords one transition diagram sheet, for identifiers combination of keywords one transition diagram, for relational operators one transition diagram. So 3 transition diagram examples are seen here. So like that, any given token we can draw their corresponding transition diagrams. Now here you can see the final example, completion of the running example. The transition diagram for the identifiers for the token number, which are the categories of unsigned numbers, is shown below. So now for identifiers with unsigned number combination, the final transition diagram is shown below. So transition diagram for unsigned numbers, so which gives the token identifier. So now here you can see, first we are starting. See the unsigned number definition you can recall once. So what we defined during starting of this lecture. Here you can see number definition, here you can see recall once. This we will use here. So it start with the digit followed with the floating point, that is dot, then again digits, then question mark, exponent, plus or minus, question mark, digits combination. So using this definition, now we are constructing the transition diagram for these numbers, that is unsigned numbers. Now you can see that one, the final transition diagram. So first it start with digit, then followed by loop, that is digit positive closure, here we have taken, it won't allow null. Then the floating point dot, then after that again digit with repetition of digits, digit positive closure, then exponent with the plus or minus. So here we are taking unsigned. After that again digit with loop, then other retract, it goes to final state. Now here you can see some alternatives also there. So if you want to continue here from digit with digit positive closure, then directly, so without floating point, if you want to take exponent value, here directly it goes to 16th state with E exponent, then plus or minus, again continues with this. So now again here you can see from 16th to without sign plus or minus, directly want the numbers, digits from 16th to here, directly it is going to 18th state with digit, followed by again digit may be repeated. That is other alternative. Next here you can see from 15th onwards, so you want to halt. So here digit closure, point digit closure, then you want to halt, you don't want exponent, directly it is going to the final state with the retract forward pointer. So then directly you want to halt by taking digit combinations repetitions, then it goes to directly other final state with the retract the forward point. So this is the final running example transition diagram for unsigned numbers with all combinations. So finally, in the definition of unsigned number token definition using regular definitions. So the transition diagram allows with all possible combinations. So like that, you have to take each and every transition labeled with the respective symbols included in the definition of regular expression. Then another transition diagram for white space. What white space contains delimited others, so like tab, new line, etc. For this, the transition diagram is shown below. Now here, first it start with starting state, then delimiter, then the delimiter may be repeated loop, then it goes to halting state, other. That is final accepting or final state. So with asterisk. This is the transition diagram for white space. So then coming to the last concept, architecture of a transition diagram based lexical analyzer. So now we discussed about transition diagram concept, representation of tokens. Now that will be treated as architecture of a transition diagram based lexical analyzer. There are several ways that a collection of transition diagrams each can be used to build a lexical analyzer. So regardless of the overall strategy, each state is represented by a piece of code. In the transition diagram, each state is represented by a small skeletal code. We may imagine a variable state, that means whatever the state that contains a variable, holding the number of the current state for a transition diagram. Here we will assume. Then a switch based, that means by using a switch case, a switch based on the value of state takes us to code for each of the possible states where we find the action of the state. That means architecture of a transition diagram based lexical analyzer is nothing but implementation of the transition diagram using lexical analyzer, using the coding that can be developed using any of the languages. Then often the code for a state is itself a switch statement or a multi-way branch that determines the next state by reading and examining the next input character. Here we will see one skeletal sample algorithm for the pointer forward based on the switch case with case wise a particular state. So that is shown here. So example, sketch of implementation of relational operator transition diagram. Relational operator is the token. This transition diagram you can recall once for relational operators and that states. So for that the algorithm we will demonstrate here. So this diagram you can keep in our mind. Starting state 0, 0, 1, 2, 3, 4, 5, 6, 7, 8. Total 8 states are there. Using switch cases, we will consider all these states and returns the respective token value. So now here you can see we'll use the method get relational operator, then we will define token get relational operator. Here token return token, we are defining another method which returns new relational operator. Then while by default take the 1, repeat the character processing until a return or failure occurs. Now here we will use switch state. Case 0 first we will take. Let us define C equal to next character. Then if C equal to less than, so less than symbol, that means it goes to what is the next state 1. Else if C equal to after less than equal, then it goes to the state 5. Then if the character is greater than, it goes to state 6. Else fail. Lexem is not a relational operator. Then break like case 1. Similarly, you can define all the cases as per the transition diagram of relational operator. Finally, the last one, retract. We'll use the method for retract, same name. Retract, it returns token. Return token dot attribute equal to what is the token name that returns? Suppose here greater than means this one. Then returns the token, return token. So like that, for all cases. Here, how many cases we have in the transition diagram? Here you can see. So here, first less than, this is case 1. Then not equal, case 2. Then less than, only less than, case 3. Then here, simply equal, case 4. Here, greater than equal, case 5. Then here, greater than case 6, and so on. Like that, all possibilities needs to include in switch case. So this is one example sketch of, that is skeletal code of implementation of relational operator transition diagram, like keywords, like unsigned numbers. For all these, the code looks in a similar fashion, but you can use their corresponding regular definition. Okay, now let us move to summary of this lecture. Here, what we discussed as part of recognition of tokens. First, we discussed about the concept of transition diagrams, then what the transition diagram contains, what states denotes, then what edges denotes, then how to represent initial or start state, how to represent final or accepting state, then how to represent edges and how are labeled by the edges. Then transition diagram for we discussed for relational operators. Then some identifiers followed by keywords, then keywords separately, then recognition of reserved words and identifiers. For all these, examples are demonstrated. Then the lastly, architecture of a transition diagram based lexical analyzer. Here we demonstrated one sketch of implementation of the token relational operator transition diagram. Okay, now I stop here. Next lecture we will come up with our next topic, which is most important topic, lexical analyzer generator, which is called as Lex tool. Then for this lecture, the reference of second edition, section 3.4, you can refer whatever we discussed in this lecture.